Hello and welcome to this Copernicus Marine Service training workshop dedicated to the Mediterranean Sea. My name is Ergan Fouché. I work at Noveltis as an ocean engineer and I'm going to be your trainer for this session. In the frame of this workshop for the Mediterranean Sea, 2 Jupyter Notebook exercises have been developed. The first one was dedicated to beginners. In this exercise, we learned how to access the Copernicus Marine Service products. We learned how to use netcdf files within Python, and we also learned how to create basic plots and figures in Python. So this first exercise has been presented during the live session of the workshop. It has been recorded and the video is available on YouTube and on the Padlet. And so on this video we're going to have a look at the second exercise, which is dedicated to advanced users. And this exercise covers a real case scenario, subjects which affects the Mediterranean Sea, which is the marine heat waves. Before we start, here is a quick reminder on how to use the Jupyter Notebook. So it consists of code and text cells. If you want to run a code cell, you can click on the arrow on the top menu or use the keyboard shortcut Shift and Enter. And if the notebook stops working, you can try to have a look to restart it by clicking on the loop arrow on the top menu as well here. Let's have a look at the agenda of this session. So we're going to have first a quick introduction on the marine heat waves. Then we're going to set up Python and to present the product we'll be using. We're going to pre-process the product in order to use them and to study the marine heat waves. And then we will make several diagnoses in order to detect and characterize the marine heat waves in the Mediterranean Sea. Right after the conclusion, I'm going to propose you several exercises for you to manipulate the product and the library we will be using, and to become more familiar with Python. So, the marine heat waves are a phenomenon that consists in abnormally warm weather. It occurs in the atmosphere, and the atmospheric heat waves are very well-known phenomena. They have been studied for decades now. However, the heat waves also occur in the ocean. They are called marine heat waves. And this phenomena, however, have been studied since 2016 only. The first definition has been given by Hope Day in 2016, and the definition of a marine heat wave is that a marine heat wave is a period of at least 5 days when the sea surface temperature is above the 19th percentile threshold of the sea surface temperature climatology. This is the definition that we're going to use in this exercise. And so, because this phenomenon has been studied for some years only, this phenomenon is still not fully understood. And this is one of the reasons why it's important to study it now. The Mediterranean Sea suffers from many threats, among which we can mention the plastic pollution, shipping and fishing, and as well in the frame of climate change, the Mediterranean Sea is getting warmer and saltier, and these changes happen at a faster pace than many other regions in the world. So due to this climate change, the marine heat waves also occur more often in the Mediterranean Sea than in the other regions. And because the Mediterranean Sea hosts many marine species, it has a very rich ecosystem. Well, these marine heat waves can have dramatic consequences on this ecosystem, but also on the activities and the economy linked to this ecosystem. And we can mention the aquaculture, for example. To study the marine heat waves, the Copernicus Marine Service catalog can be very useful because the products, so either the model products or the satellite observation products, have very long temporal resolution, and therefore we are, well, thanks to these long time series, we're going to study the changes and we're going to study very long periods. The figure here has been created by the SACIB app dedicated to the Mediterranean Sea indicators, and it shows that the marine heat wave maximum intensity kept increasing in the past 40 years. So here on the left we have the maximum intensity in Celsius degrees, and on the bottom we have the years. Before we start our analysis, we need to set up Python, because the Jupyter notebook needs to be initialized just like any other Python environment. And so here is the list of the libraries we're going to use. We're going to use NumPy first, which is a very basic package for scientific computing. We're going to use Xarray, which is the library we use to manipulate netcdf files. We're going to use Matplotlib for, well, to plot figures. We're going to use Cartopy for maps and geospatial data analysis. We're going to use datetime to manipulate dates and times. And finally, we're going to use a library which is entitled Marine Heat Waves. The script of this library is available in the same directory as this Jupyter notebook. And so this module implements the definition of the marine heat waves that was given by Hobday in 2016. And this is the library we'll be using. It offers plenty of functions to study the marine heat waves. So here in this cell we import all the libraries that we are going to use. Now that we've presented the libraries, we're going to present the product we'll be using. So we're going to study the sea surface temperature thanks to a satellite observation product which is entitled Mediterranean Sea High Resolution L4 Sea Surface Temperature Reprocessed. Here you have the link to the page on the Copernicus Marine Service catalog. On this page you can find all the informations, all the characteristics of the model. This model has daily means of the sea surface temperature. The spatial resolution is of 0.05 degrees. The temporal coverage goes from 1982 to 2021. This is the geographical extent. You have here the description of the product, and as well you have the documentation, so the product user manual and the quality information document. That's it for the product we'll be using. we can now start to use these files. So in the definition given by HopeDay, it's advised that we use at least a 30-year-long time series. In this exercise, however, we're only going to use a 20-year-long time series. All the data that we're going to use are already, well, they have already been downloaded and they are stored in the data folder here. We have split the files, so the time series, into 4 files of 5 years each. So the first one, for example, goes from 2001 to 2005. The files have been renamed accordingly. So the first one here is entitled according to the period that it describes. And we have split the file into 4 files because on the Copernicus Marine Service catalog you can only download files which size are of 1 gigabyte maximum. So this is why we have split the file into 4 subfiles. Let's have a look at one file to see how it's constructed and what kind of variables it contains. So we can see that the dimensions and coordinates are time, latitude, and longitude. We do not have depth as dimensions or coordinate because we only study the surface temperature. If we have a look at the attributes of the variable analyzed SST, we can see that this variable refers to the sea surface temperature and that its units are Kelvin degrees. In the next cell, we're going to convert Kelvin degrees into Celsius by subtracting 273 to the first variable, and to create doing so we're going to create a new variable. So we assign to the dataset a new variable which we called analyze SST underscore C for Celsius, and we also assign attributes to this new variable. We put the long name, analyzed sea surface temperature, we put the units which are now Celsius degrees, and we add a comment to explain how this new variable has been calculated. If we check on this new dataset variables, here we can see that we now have 2 variables, the first one in Kelvin degrees and the second one in Celsius degrees. Now we're going to create a map of the sea surface temperature, so taken from this file. For each of the figures I'm going to present you, first I will show you the figure and then I will explain you how it's been constructed. So here is the first map we create. This is the sea surface temperature on June 2020. The color refers to the temperature, and it enables to locate the coldest and the hottest regions in the Mediterranean Sea. So how did we construct this figure? First we define the date, so here June 2020. Then we select the product at this date. Then we can create the figure, so we create the figure and we define its size. We add the axe and define the projection of the map. We add the coastline, we add the grid line, so latitude and longitude. We remove the longitude and latitude labels on the top and on the right. We add the land mask and we set the extent of the map. To display the temperature on the map, we use the matplotlib function pcolor, and we use the variable temp map that we have created just before. We set the min and max values of the color bar, and we also set the color map, the colors in which we want to display the temperature. Then we add the subtitle, the color bar, and the title of the color bar, and finally we save the figure. So this figure has been created thanks to a dataset, to a file which contained 5 years of data. But as I said before, we need to study, in order to study the marine heat waves, we need to have longer periods, and therefore we're going to have to create a 20-year-long time series of the sea surface temperature. As I said before, all the files, the 4 files that we're going to use, are stored in the data folder. So the first thing we need to know is to list the files that we are going to use. So this is what this cell does. We put in a list all the files that we want to use. We define a small function to convert the Kelvin degrees into Celsius degrees, just like we did before. And then we can open all the files and store them into one only dataset using the xarray.openmf dataset. So we put the input arguments are the file name, so the list we have set before, and we also use the preprocess function that we have defined before in order to convert, again, the kelvins into Celsius. If we have a look at the output, we can see that indeed the time from this new dataset goes from 2001 to 2020, so it has done what we wanted. Yet, if we have a closer look at the analyzed SST variable, we can see that the data is split into chunks, which is not a structure we're used to, and therefore we're going to have a small operation in order to go back to the right format. So what we do is that we save it into a netcdf, and then we open the new netcdf. So the netcdf, the complete netcdf file is stored in the data time series folder. And if we open it again, we can see that we have a very clean dataset with the right period, so from 2001 to 2020. We have the analyzed SST in Celsius degrees, and we are now all set to begin our study. So as I said before, we are going to study the marine heat waves thanks to a Python library which is entitled Marine Heat Waves. And if we have a look at the script, we can see, this is not the script, sorry. We can see that it consists of many functions. If you want to find the documentation of these functions, you can have a look at the documentation or at the script. You have plenty of information on the function and on the capacities of this library. And so the main function is the marine heatwave.detect function. So as the documentation states, this function applies the Hopday and Al marine heatwave definition to an input time series of temperature along a time vector. And the output properties of this function, well, the output of this function is the properties of all the marine heat waves identified over the periods. So if we have a look again at the script, we can see the outputs that can be calculated. So we have the the time of the marine heat waves, the time at which the marine heat wave started and ended. We have the time of the peak, etc. So you have plenty of information. But before we use this function, we need to calculate the average sea surface temperature over the whole Mediterranean Sea basin. And so to do so, we use the function .mean from X-array. We specify the dimensions. So here we calculate along the average along the longitude and latitude. And so if we display the result of this function, we can see that we now only have the sea surface temperature, which depends on the time. And we can, well, this is what we will need for our function, sorry. We can store this variable into the temp Python variable, and now we can work on the time variable, because the marine heat wave detect function expects to have an input time in the shape of datetime.date format, and what we have in the X-array dataset is datetime 64 format. So we need to make a small operation again in order to convert into the right format. So this is what we do here. We put into a list all the date times included in our dataset in the right format, and if we check, we can see that this is the good format. So we are now all set finally to use the marine heat wave detect function. This is what we do here. So as we said before, the inputs are the date in the right format and the sea surface temperature, so the time series of the average sea surface temperature over the whole Mediterranean Sea. And the outputs are so the marine heat waves characteristics and the climatology. If we have a look at these two outputs, well, they are both directories, Python directories. We can find all the arguments that were described in the documentation and the library script. So we have the time the start time of each marine heat wave identified, the end time, etc. Regarding the climatology keys, we have the time series of the threshold, the time series of the climatology, for example. We remember that the threshold has been defined by the 19th percentile of the climatology, the sea surface temperature climatology. So these are the keys of the output of the detect function. We can, for example, have a look at the number of events which occurred during this period. So this is what this cell does. It prints a small sentence which states there has been 37 detected marine heat waves events in the Mediterranean Sea between 2001 and 2020, sorry. So that's for the number of events. We can also have a look at the most important event. What we do in this cell is that we get the index of the event which had the maximum intensity, and then we print its characteristics. And so, for example, we can see that the maximum the event which had the maximum intensity happened from June 2003 to July 2003. It lasted for 25 days. Its maximum intensity was of almost 2 degrees above the threshold. and its average intensity was of 1.5 Celsius degrees above the threshold. So this marine heatwave event from 2003 occurs in the sea, obviously, but it's better known in the atmosphere, because in Europe in summer 2003 there has been a huge heat wave, and this event is very well known. It is still a reference regarding the weather. So in the following cells we're going to focus on this particular event. We're going to plot a figure. So as I did before, I'm going to present you the figure and then how we built it. So on the first figure we have the time series of 3 variables. So first, the sea surface temperature recorded by the satellite product. Then we have the seasonal threshold, so with the definition of the 19th percentile of the climatology. And then we have the climatology. So the sea surface temperature is in black, the threshold is in green, and the climatology in blue. The second figure shows, is a zoom of the first one over the year 2003, and the marine heat waves appear in red and in orange. In red it's the most important one, and in red it's a second one which followed the first one. So how did we create this figure? First, we created the figure, defined its size, and defined the 2 subplots. Then we plot the 3 parameters. So the sea surface temperature, we plot it from the observation product, the file we created before. Then we plot the threshold. This is an output of the detect function we used before, and then we plot the climatology. Again, it's an output from the detect function. Then we add the properties of the axe. So we set the title, we add the legend, we set the limits of the x and y axis, and we add the label of the y axis. Then we do the same for the second subplot. So the following these lines enable to add the color to identify the marine heat waves. So this is what it does. Then we plot, just like we did in the first subplot, we plot the sea surface temperature, the threshold, and the climatology. We add the properties of the axe, so the title, etc., and then finally we save the figure. So in this figure we can clearly identify the marine heat wave which affected the Mediterranean Sea in 2003. We can see that this first marine heat wave was followed by a second marine heat wave, and we have to remember that this diagnosis, this first study we are making, in this study we are considering the whole Mediterranean Sea. We have been calculating an average on the whole basin, and in the next section we are going to see how relevant it is to study sub-regions of a sea compared to the whole Mediterranean Sea, because obviously the marine heat waves do not affect all the regions equally. And so in this section we are going to split the Mediterranean Sea into 2 regions, the eastern region and the western region, And we're going to apply the same operation as we did before on each of these regions. So first we select we subset the file in order to have our two regions. Then we calculate the average of the sea surface temperature on each of these regions. And just like we did in the previous section, we display the number of events which occurred in each of these regions. So the result is not very surprising here. We can see that there has been 37 detected marine heatwave events in the western part and 37 events in the eastern part as well. So that's it for the number of events, but we can now study the intensity of the events. And so this is what we're doing now. It's again the very same script that the one we used before. So on the western part, we can see that again it's the event from 2003, which was the most intense event in the western part. However, this event in 2003 did not really affect the eastern part. However, the most intense event in the eastern part happened in 2018, and it lasted for over, almost 2 months. So this is an example, a very brief example, which shows how important it is to study local dynamics and not only global regions when we study the marine heat waves. So in this last section, we're going to show you a last diagnosis you can make to study the marine heat waves in the Mediterranean Sea. We're going to study a smaller region, which is the Gulf of Taranto in southern Italy. We're going to study statistics of each pixel of each cell computed in the product, the satellite observation product, and we're going to study for each cell the statistics, so the number of events, the number of days affected by marine heat waves, the maximum intensity for each cell, each pixel of the product. So before we learn how to do it, here is the result for you to understand what we're making. So here on the left figure, the left map, we have the total number of days of marine heat waves in 2020. So yes, we are now only studying the year 2020. We can see that in this year, during this year, there has been, in some regions, 14 days of marine heat waves, and in some other regions, none. On the second figure, the second map, we have the average maximum intensity of marine heat wave in 2020. And in the last one, we have the number of marine heat wave events in 2020. So how did we create this figure? So first, we subset the data set in the region we're interested in. We can see that we have subset the latitude and longitude, and that's it. And then we initialize the arrays. So the objective of the following cells is to create for each pixel, to compute for each pixel the statistics and to put it back into an array that we're going to display on a map. So here we initialize the arrays. Then we are making the loop over each pixel, so along each latitude and along each longitude index. We calculate the statistic thanks to the detect function. So because we're having, and then we put back the statistics into the arrays we have initialized before. So because we're making a loop over each of these pixels, the process of it can take some time. And here we display how advanced the running is. So now that everything has been calculated, we can plot the characteristics. So we have 3 subplots, which have the same projection. For each of these subplots, we define the characteristics, the same ones that we did before. Then here we plot the number of days thanks to, again, the output of the detect function. So in the first map we plot the number of days which were affected by a marine heat wave. In the second plot we have the maximum intensity of the average maximum intensity of each cell, and in the last one we have the number of events, the number of marine heat waves which happened during the year 2020. So here is the result, and these figures are very interesting. They illustrate very well how important it is to consider some region and not only the whole Mediterranean Sea, the whole basin, regarding the marine heat waves. All the regions are not affected equally. The coastal regions here are much more affected by the marine heat waves than the other ones. And so that's it. This was our last diagnosis. So let's have a brief conclusion to remind us of what we have learned in this notebook. First, we have studied, thanks to the Python library Marine Heatwave, we have studied the characteristics. We have identified the marine heat waves which occurred from 2001 to 2020 in the Mediterranean Sea, so over the whole Mediterranean Sea. Then we have split into two regions, the eastern part and the western part, and we have again calculated the statistics of the marine heat waves on each of these regions. And then finally we have studied a much smaller basin, the Gulf of Toronto, and we have computed the statistics of each cell available in the product, so the satellite observation product, in order to observe the differences between the regions. In order to manipulate the codes that I've presented to you, we propose to you a set of exercises with several levels. We have exercises for beginners, intermediate level users, and experts. So the first exercise, in the first section, we plotted a map for a map of the sea surface temperature in June 2020. So you can try to change this date and to display the sea surface temperature at another date. In this section, we have split the Mediterranean Sea. Over the whole exercise, we have studied a 20-year-long time period, but you can try to add some other files and to study a longer period, maybe to follow the advice of 30-year long time periods. Maybe you can do this. Then you can try to analyze some other regions. We have split the Mediterranean Sea into 2 parts, but you can try to split into some other regions, and you can try to study another small basin, such as the Gulf of Toronto. And finally, the exercise for experts. In this cell, we have created a loop on each of the pixels. However, in the Jupyter Hub environment, you cannot parallelize the code, so you have to create the loop. But if you work on your own infrastructure, you can try to parallelize the code in order to have a quicker result and to study larger regions. So this is one of the things you can do. We have not put the correction of these exercises in the notebook. However, if you struggle with some of them, you can ask us a question, send us an email at the servicedesk.simems@mercatorocean.eu, and we'll be very, very happy to answer it. So this is the end of this video of this Jupyter notebook. I would like to thank you very much for your attention. I really hope you enjoyed this notebook on the Mediterranean Sea. You now have plenty of material, of codes to study the Mediterranean Sea and the marine heat waves. Do not hesitate to reuse them for your own needs. With other products, we have used here satellite observation, but you can use model products as well. Do not hesitate to adapt these codes and this notebook. And if you have some questions or some suggestion, again, do not hesitate to contact us at this email address. Thank you very much again. I hope I'll see you soon. Bye.